Hi everybody. Today we're just going to talk a little bit more about Newton's law of universal gravitation. You've already seen the equation in class. You understand about the force due to gravity, and in your simulation you've been trying to figure out your universal gravitation constant. So now for the objectives for this lesson, we're just going to understand how the mass of the objects and the distance between them affects the size of the force of gravitational attraction between them, and then use Newton's law of universal gravitation to determine some of the size of these forces of attraction between objects due to gravity. Okay, so here's our Newton's law of universal gravitation. You've already seen it. We know that the force of attraction due to gravity between objects is equal to g, that universal gravitational constant, multiplied by the masses of the objects, divided by the distance between their centers squared. If you haven't come up with an experimental value of g yet using your graphs in class, here is what g is equal to: 6.67 times 10 to the minus 11th Newton meter squared per kilogram squared. Kind of a weird unit, but you'll see that the meter squared cancel out with the distance squared, kilogram squared cancel out with the two masses, and you're left with newtons. This is a sort of a fudge factor constant, and you can see it's a relatively small number. So as a result, this is why we don't see the effect of the force due to gravity on objects until these numbers get really big. All right, the last thing you want to remember is that r. It's the distances between the centers of the objects. You might think that when you're sitting here on Earth and you're talking about the gravitational force between two baseballs, that the distance between their centers and their surfaces isn't going to make much difference. And that's probably true. But when you start to talk about celestial objects, moons and planets, their radius is so large that it adds significantly to the distance between the two objects when you look at their centers compared to their surfaces. So you always want to make sure that you realize that should be the distance between the centers of the objects. Newton tells us that the gravitational force between objects is one of attraction. That means they're always trying to pull each other towards each other. Newton's third law tells us that the size of the force exerted on each object is the same but opposite in direction. And that makes sense even when we look at the math. If we're looking at the force on object 2 by object 1, or the force on object 2 by on object 1, I think I said that right, the math is still the same. You're still multiplying the same two masses. So the size of the force is the same, it's just that the direction is opposite as they try to pull each other towards each other. And the universal law of gravitation is known as an inverse square law. We all know what an inverse relationship is. As one goes up, one factor goes up, the other factor goes down. So in this case, as the distance between objects increases or goes up, the size of the force between the objects goes down. A little bit different in this one is it's an inverse square, which means there's a square along with the distance in the bottom. So as a result, that force between objects as the objects are moved further apart decreases much more rapidly than if the square didn't exist. So it's still an inverse relationship, but it tells us, for example, when we double the distance between objects, we 1/4 the size of the force between them. Let's look at a few examples. Here we have two bowling balls, and we're just looking at the size of the force exerted by bowling ball A on bowling ball B. We would also know that the size is equal and opposite if we look at the other situation of the bowling balls. So let's write down our Newton's law of universal gravitation. Okay, so we have G equals 6.67 times 10 to the minus 11th Newton meter squared per kilogram squared, right? Times our two masses. Our bowling balls are identical. Each one is 7 kilograms. Divided by the distance between their centers squared. So 2 meters squared. So we get the size of that gravitational force is equal to 8.2 times 10 to the minus 10th And let's just make sure they're really newtons. Kilograms. This is a kilogram times a kilogram, so it's going to cancel out one of them. The other kilogram will cancel out that one. This meter here, not only did we square the 2, but we squared the meters. So that meter squared will cancel out with the meter squared up here, and we are left with newtons. So that's the size of the force between those two bowling balls, and as you can see, that is a really, really small force. Times 10 to the minus 10th means we move that decimal point over 10 places. So that's really small, and most gravitational forces are pretty small. It's a very weak force. Okay, let's look at another one where we increase our size and start going out into space. So now we're looking at the gravitational force of attraction between two asteroids. And you can see that the masses of these are much greater than the masses of our bowling balls. So let's see what happens to the size of the force between them. So again, we write down our law of universal gravitation. Multiply it by our two masses. Both our asteroids have the same mass here. So you could either do this as 25,000 kilograms times 25,000 kilograms, or you could just square it. All divided by the distance between their centers. We would assume that that's how it was given to us, as the distance between their centers. And we end up with the size of that force is 2.4 times 10 to the minus 9th newtons. And you might think, wow, that is not significantly greater than the force that was between the two bowling balls. But these things are so massive. Well, also look what happened. The distances between them is also pretty massive. So as a result, you still have a very small force due to gravity between these two objects. I'm going to make some couple recommendations about problem solving. Just because I said that this unit does tend to get a lot of students on their math. So we want to make sure that we're doing things as best we can to not create those problems. So the first thing is rearrange your equation all the time whenever you can, and wait until the end to plug in your numbers into your calculator. So say, for example, you were looking for the distance between the centers of two objects. Given this equation, watch trying to just plug in numbers and then stick it into your calculator by not rearranging first. If I wanted to find the distance here, I would rearrange this guy this way, and then I would know I would have to take the square root at the end. It's a lot easier just to plug in that into your calculator when you know what you're doing and wait until the end. If you use scientific notation or even all the zeros, there's a lot of tendency to make mistakes as you go from one step to the next if you're retyping in things into your calculator. So if you can wait as long as possible to start doing your solution, it'll help prevent some of those mistakes. Watch your units that you're given in the problem. Most of the objects, their masses are given in kilograms, because kilograms is that standard unit of measurement for the metric system. Distances are usually very large, and even though they're given in scientific notation, that doesn't necessarily mean that they're given in meters. They have to be in meters. Often they are given in kilometers, which means that you have to convert to meters. Remember that there are 1,000 meters in every kilometer. So even if you're given a unit of length, say this one, in kilometers, the change to meters is simple. When you multiply by 1,000, you just add 3 to this number. So you would say 6.2 times 10 to the 9th meters. The next thing is use your calculator wisely. It's a great tool. But if you're still doing a lot of the times 10 to the caret something, you're introducing a lot of levels of math where you've got to worry about order of operations. Please use that EE function to put numbers into your calculator in scientific notation. If you have one of the Texas Instruments calculators like this, it's that second function button, and the number above the key above the 7 number is where you will get that EE function. If you do the coefficient, second EE, it'll put that E down there in your screen. You just put in the exponent after that, positive number or a negative number, whatever it is. But that'll help clear up some problems that you might have with order of operations and getting the wrong answer. And then the last thing you want to do is always ask yourself, does it make sense? Objects in space are usually pretty big, so you're not going to get the mass of a moon to be equal to 6.2 kilograms. All right, that's just not going to happen. If you're looking at it is 15 pounds, it's just not going to happen. All right, and they're usually pretty far apart. So again, you're not going to get a distance between their centers to be about 9.3 meters if we're talking about objects in space. You're talking about really big numbers. So again, always ask yourself at the end of a problem if it makes sense. Okay, with that, let's do one more example. We have the Earth that has a mass of 5.97 times 10 to the 24th kilograms, the Sun, and the distance between them. Most of the time, unless you're told that it's not the distances between their centers, somehow you're told it's the distance between their surfaces, you can be pretty sure that a problem gives you the distance between the centers of the objects. And this problem asks for the size of the gravitational force that the Earth exerts on the Sun. Well, we can figure that out, and we would also know that that's the size of the gravitational force that the Sun exerts on the Earth. So let's give that a try. So here we go. So let's look first. We have our equation. You can start to see this is where some of our numbers get really big. So you're going to have to be careful with how you put information into your calculator. So my G is still 6.67 times 10 to the minus 11. Newton meter squared per kilogram squared. We're going to multiply our first, which is we're going to say is the mass of the Earth, 5.97 times 10 to the 24th kilograms. And the mass of the Sun, 1.99 times 10 to the 30th kilograms, all over the distance between them squared. Alright, so it tells us that the distance is 1.5 times 10 to the 8th kilometers. Have to make sure that's in meters. So I'm just going to do the shortcut of 1.5 times 10 to the, and add 3 spaces to my 8, which would be 11 meters squared. Alright, a huge amount of math in there. You can see that there's a lot of opportunity to make some errors when you put this information into your calculator. If you have any problems, please come and ask because we can help you out. So when we look at that, we get finally a number that's actually pretty sizable. 3.5. Not only is it pretty sizable, it's pretty enormous. Times 10 to the 22nd newtons. So you start to see that the only way to get really appreciable forces between two objects that are really far apart is to have really big objects. Alright, the last little thing we want to look at is how does changing the mass or the distance between the objects change the gravitational force. Now you can see a lot of times that you don't want to have to recalculate these numbers all the time. If you just know maybe the mass of one and you change the mass of another, or you change the distance, sometimes it's easier if we just write it in terms of algebra. So let's say, for example, we have the force of gravitational attraction between two objects, one of mass 1 and one of mass 2, at a distance of r between their centers. What would happen to the size of the force? What would the gravitational force be if we took one of the masses and made it 3 times bigger? So we made it 3 times bigger, mass 1. Well, hopefully you would see that the gravitational force would increase, but instead of having to go and recalculate everything, Sometimes what we can do is we can say, well, this new gravitational force with this bigger mass and everything else staying the same is going to be G times 3m1 times m2 divided by r squared. And what we do is if we pull that 3 out the front, we actually end up with this saying that it's equal to 3 times G m1 m2 which happens to equal 3 times the original force due to gravity that existed between the objects. This is just a way of being able to use algebra and the factor that we change objects, mass or distance, in order to be able to see how it changes the resulting force. You may not know the size of any of the objects or even the size of the force, but you can say how much bigger or smaller the force would be depending on how much bigger or smaller the masses were. The relationship between mass and gravitational force is direct. So if the masses go up, the size of the force between them go up. If the masses go down, the size of the force between the objects goes down. Now, what if we change the distance? So say, for example, again, we had the force due to gravity between two objects was equal to our universal gravitation equation. And then say we doubled the distance between them. So we keep our masses constant, but we double the distance between their centers. And we want to know how that's going to affect the force of gravity between them. So again, we're going to say, well, this new size force of gravity is going to equal G m1 m2. The masses didn't change. And now if I double that, that becomes 2r, that whole quantity squared, right? And we end up essentially here with G m1 m2. Remember, we square everything in the expression, so that becomes 4r squared, which is essentially 1/4. If we pull that 1/4 out, G m1 m2 over r squared, which is essentially equal to 1/4 of the original force due to gravity that existed between the two objects. So it's just showing that relationship now of when we change the distance between two objects, the closer they get together, the larger the force will be. The further apart they get, the smaller the force will be. So again, you don't need to know any of the individual masses or distances, but you can figure out relationships if you know about by what factor you multiply any of the variables. Okay, hope that helps with starting your problems.